Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Hello, and welcome back to the show. We're absolutely thrilled to have you with us today because we are looking up.
Way up.
Exactly. We're turning our gaze toward one of the most baffling, high-energy mysteries in the entire known universe. We're talking about a phenomenon that has basically been taunting astronomers for, nearly 2 decades now?
It really has. I mean, it's one of those cosmic puzzles that just, refuses to fit into the box. It has kept a lot of very smart people awake at night just staring at data screens.
We're talking, of course, about fast radio bursts.
Or FRBs, for short.
I've always loved that name, fast radio bursts.
Yeah.
It just sounds so urgent. It sounds like a warning. And the description, it really matches the name, right? These are essentially cosmic flickers.
Flicker is a good word, but it almost understates the violence of it. These are millisecond-long flashes of radio waves. They appear out of nowhere. They just scream across the cosmos with this incredible brightness.
And when you say incredible, you mean?
I mean, releasing as much energy in a fraction of a second as our sun does in days or weeks, or for some of them, even a century.
A century's worth of solar energy in a millisecond.
And then what? They're gone. Silence.
That is the part that gets me. Every time we discuss this topic, the sheer scale of the energy versus the brevity of the event, it's like a camera flash that blinds you from across the room.
Mm-hmm.
But the camera is actually located in another galaxy entirely.
That is a fantastic way to visualize it. And because they're so bright and so short, for the longest time, the big question, the obsession really has been, what is the engine driving these things? What kind of cosmic beast has the power to scream that loud, that fast?
All right. It's the classic celestial whodunit. Are they, lonely, isolated stars just screaming into the void?
Is it a cataclysmic explosion where something is being destroyed?
Or is there something more complex, maybe even more structural going on?
It has been a massive open question in astrophysics. For a long time, there were more theories than there were observed bursts.
But that's changing. And that's why we're here today. We're unpacking a major break in the case.
We are. And this isn't just a theory or some computer simulation running in a basement somewhere. This is, the paper calls it decisive evidence.
Okay.
Published just recently on January 16th, 2026 in the journal Science.
And this comes from a huge international team, right?
A massive collaboration, yeah, including researchers from the University of Hong Kong or HKU. And the headline is just, it's astonishing, at least some of these FRB sources. They're not living the single life.
They are in relationships. I like that. Even stars need a plus one.
Exactly. They are in binary stellar systems. They have companions, and that changes everything about how we understand them.
So today we are starting a full investigation. We're going to unpack this discovery piece by piece. We're going to meet the detective in this story, a massive telescope called the China Sky Eye.
And we'll look at the subject, a specific repeating burst source known as FRB 220529A.
And we're going to talk about a smoking gun event, a little something called an RM flare. And just to give you a roadmap, this isn't just about finding a second star. It's about how a really boring observation, literally staring and nothing happening for months, suddenly turned into a discovery that might just change our understanding of the architecture of the universe.
It's a great story. It's about patience, the physics of light, and, stellar weather.
I love stories where boredom pays off. It gives me hope for my own life. So let's set the scene. This wasn't a lucky snapshot, was it? This wasn't someone just pointing a telescope at the sky at random and boom, they get lucky. This was a stakeout.
Oh, precisely. This is a long-term, calculated stakeout. And to understand why this is so special and why we haven't found this before, we have to talk about the tool they used, the FAST telescope.
FAST. F-A-S-T. That stands for the 500-meter Aperture Spherical Telescope.
Located in Guizhou, China. It's the world's largest filled aperture radio telescope. When we say China Sky Eye, we aren't kidding. The scale of this thing is, It's just hard to wrap your head around.
500 meters across. If you filled that dish with water, you're not talking about a pool, you're talking about a lake.
You could fit entire neighborhoods inside the dish. And in radio astronomy, size is everything.
Size matters.
It really does. The larger the dish, the more radio waves you can catch. It's like having a bigger bucket in the rain.
Right. A bigger bucket catches more drops.
In this case, the drops are these incredibly faint radio signals from billions of light years away. The sensitivity of fast is what makes this kind of detailed monitoring even possible. It can hear whispers that other telescopes might miss entirely.
So they've got this massive ear listening to the sky. And they didn't just listen to static. They pointed this massive ear at a very, very specific target.
FRB 220-529A.
Which I have to say sounds like a license plate.
It does. It's not the most poetic name. Astronomers are great at math, not always great at branding. But that license plate represents an active, repeating source. And it's located about 2.5 billion light years away.
Okay, before we go any further, let's pause on that word, repeating. Because that is a crucial distinction in this field, isn't it?
It's everything.
My understanding is that most of these fast radio bursts, they happen once, and then they never happen again.
That's right. The vast majority of FRBs we've ever detected are one-offs, a flash, and then silence forever from that spot in the sky.
And those must be incredibly hard to study.
Oh, they're a nightmare. Because you can't predict them. You don't know where to look until it's already over. It's like trying to study a lightning bolt without knowing where the storm is.
Or trying to study a car crash after the tow truck has already left.
That's a great way to put it. But a repeater is different.
A repeater is a gift.
It is a gift. It flashes again and again. It gives you a specific address in the sky to focus on. It says, hey, I'm over here, keep watching.
Which means you can keep the camera rolling, so to speak.
Exactly. Repeaters allow for long-term monitoring. You can watch them over time to see if anything in their environment changes. You can track their behavior, their patterns. And that is exactly what the FRB Key Science program has been doing since 2020.
And this program was co-led by Professor Bing Zhang, the chair professor of astrophysics at HKU?
Correct. And they decided to keep a very close watch on this one specific source, FRB 220-529A.
And this is where the human element comes in, the patience.
Here is where the patience part of science really comes into play. I think people often imagine science as these constant eureka moments happening every day in the lab.
Right, the flashing light bulbs over people's heads.
But often it just looks like monotony. For 17 months, they watched this source.
17 months is almost a year and a half of just staring.
And for 17 months, the data appeared, well, unremarkable.
Unremarkable.
Just doing its normal thing, blinking occasionally. Standard repeating FRB behavior. The signal looked clean, consistent, and frankly, a bit boring.
I can just imagine the researchers checking the data every morning. Anything new? Nope. Anything weird? Nope.
Yeah.
Just 17 months of steady as she goes. I mean, why keep looking? If I stared at a wall for 17 months and it didn't move, I would probably stop staring.
Well, you need that baseline. That's the key. If you don't know what normal looks like, you can't possibly recognize abnormal.
Okay.
You have to know the resting heartbeat of the system before you can diagnose an arrhythmia. You need the control group.
That's a fair point. You can't spot the anomaly if you don't know the pattern.
Exactly. And then, near the end of 2023, the boredom broke.
The turning point. The exciting part.
The data suddenly spiked. Something changed drastically in the signal they were receiving.
Okay, so let's unpack that change, because this is where we get into the real physics of the discovery.
Yeah.
This wasn't just that the signal got louder, right? It wasn't just a volume knob being turned up.
No, not at all. It was about the quality of the light, specifically something called polarization.
Polarization. Okay, I think most of us have heard that word, probably in the context of, what, sunglasses.
We do. That's the perfect daily life analogy. Think about light from the sun or a light bulb. Usually, the light waves are vibrating in all directions at once, up and down, left and right, diagonally. It's a chaotic jumble of vibration.
Like a crowd of people walking in every direction at a busy intersection.
Perfect.
Right.
But polarized light is disciplined. All the waves are vibrating in the same plane. Imagine shaking a rope. If you shake it up and down, the wave is vertical. If you shake it side to side, the wave is horizontal. That's polarization.
And these FRBs have, what, nearly perfect polarization?
Near 100% linear polarization. So it's like someone is shaking a rope across the universe in a very specific direction. It's an incredibly pure signal.
And polarized sunglasses, they work by blocking the waves that aren't lined up correctly.
Exactly. They act like a tiny picket fence. If you shake that rope up and down, it can pass through the vertical slats of the fence.
But if you shake it side to side...
the fence stops it. That's how they cut down on glare.
Okay, so we have these perfectly oriented waves. Let's just say they're vibrating up and down. And they're traveling through space for 2.5 billion years. They're headed toward Earth. What happens to them on the way?
Well, space isn't perfectly empty. especially not the space right around the source of the burst. As these radio waves travel, they might pass through what we call magnetized plasma.
Magnetized plasma. That sounds like something from a sci-fi weapon.
It sounds exotic, but it's actually one of the most common things in the universe. Plasma is just a gas that's been superheated until the electrons are ripped off the atoms. It's a hot, charged soup.
Okay.
And magnetized just means there's a magnetic field running through it.
So we have our rope wave traveling through this hot magnetic soup. What does the soup do to the rope?
It twists it.
It twists it.
It rotates the angle of the vibration. This effect is called Faraday rotation. So if the wave started out vibrating up and down after passing through the magnetized plasma, it might be vibrating diagonally or even completely side to side by the time it gets to us.
So the plasma literally grabs the wave and physically spins the orientation.
That's a great way to think of it. And the more dense the plasma is, or the stronger the magnetic field, the more it twists. And we can measure that twist.
Wow.
We use a metric called the rotation measure, or RM for short.
So the RM is basically a number that tells you how much has this signal been twisted by the stuff it flew through to get to us.
That is a perfect summary. The higher the RM number, the more stuff it flew through, or the more magnetic that stuff was.
Okay, so let's go back to our stakeout. We have 17 months of data from FAST.
And during the 17 months, the rotation measure, that amount of twist, was pretty constant. It had a steady, low value.
Which tells us the environment around the FRB was stable.
Very stable. The light was passing through the same amount of stuff every single day. Normal, boring, predictable.
And then came late 2023.
Enter Dr. Yi Li from the Purple Mountain Observatory. Dr. Li was analyzing the data and noted an abrupt, massive increase in the rotation measure.
How massive every time? Did it double? Triple?
Yeah. It increased by more than a factor of 100.
Whoa. Okay. That is not a blip. That's not a measurement error. That is a fundamental distortion.
It was a massive distortion. The signal was being twisted wildly compared to what they'd seen for the last year and a half. And here's the key piece of evidence. This spike didn't stay forever. It rapidly declined and returned to normal over a period of just 2 weeks.
So 17 months of normal, 2 weeks of extreme twisting, and then right back to normal.
The team dubbed this event an RM flare.
An RM flare. It sounds dramatic. So let's put on our detective hats here. If the twist comes from passing through plasma, then a sudden massive increase in the twist means that a very dense, very magnetized plasma suddenly crossed the line of sight between Earth and the FRB.
That's the only logical conclusion.
I like analogies.
Yeah.
So is this like,
Yeah.
Imagine we're looking at a flashlight beam. That's the FRB. And for 17 months, the air between us and the flashlight is clear.
It's perfectly clear.
And then suddenly, a thick cloud of smoke blows right across the beam.
That is a great analogy. The smoke would distort the light, make it shimmer and change. In this case, the smoke is a clump of magnetized plasma. And because it only lasted 2 weeks, we know that this clump was moving, it crossed the path and then cleared out.
So we have a smoking gun, or maybe a passing cloud of plasma. But where did the plasma come from? The FRB is 2.5 billion light years away. We can't just send a drone to check it out.
No, we have to deduce it. And this is where we move to the next phase of our investigation, identifying the culprit.
Connecting the dots. Okay, we have twisted radio waves. We have a temporary cloud of plasma. How do we get from that to binary star system? I mean, why couldn't it just be a random cloud floating by in deep space?
It comes down to probability and physics. Deep space is actually pretty empty. The chances of a random, dense cloud just happening to drift by exactly in front of this one tiny source are astronomically low. You need a source for that plasma. You need an engine that produces it nearby.
You need a smoke machine to make the smoke.
Exactly. And Professor Bing Zhang provided the explanation. He said the natural explanation for a sudden plasma cloud appearing and disappearing like that is a companion star.
A neighbor.
A very close neighbor. Imagine the FRB source, which we're pretty sure is a magnetar, and we can get to that in a minute, just sitting there in space. And right next to it, orbiting around it, is another star. Maybe something massive, or maybe something more like our sun.
Okay, so they're dancing around each other. A binary system, two stars locked together by gravity.
And just like our sun, other stars are active. They aren't just calm, glowing balls. They're volatile. They have weather. Sometimes they burp.
They burp.
Technically, it's called a coronal mass ejection, or a CME. You've probably heard of solar storms.
Oh, right. We hear about those with our own sun all the time. when the sun spits out a huge cloud of stuff that can mess with our satellites or create the northern lights.
That's the one, and that stuff it spits out is a massive clump of, you guessed it, magnetized plasma.
There it is.
So the scenario they propose is this. The companion star launches a CME, a big blob of plasma. This blob physically moves out into space. And in this specific case, its path took it right in front of the FRB source from our perspective.
So it moved right between us and the FRB.
Exactly. It didn't block it completely, but it put a very dense, magnetized filter in front of it. The radio waves from the FRB had to pass through this fresh blob of plasma to get to Earth. That causes the massive twist, the RM flare.
And as the blob keeps moving on its trajectory,
the distortion fades. And after about 2 weeks, the coast is clear, the blob has moved past our line of sight, and the signal goes right back to normal.
That is incredible detective work. You're watching a tiny blip of light, you see it get twisted, and from that you realize, oh, the guy standing next to him and just sneezed.
That is effectively what happened. A stellar sneeze.
Yeah.
And the math backs it up completely.
This is where Professor Yuanpei Yang from Yunnan University comes into the picture, isn't it?
Yes. Professor Yang ran the numbers. They calculated the size and the density of the plasma clump that would be required to cause that specific amount of distortion they saw. And it matched perfectly with the known properties of CMEs launched by our own sun and other stars we've studied in the Milky Way.
So it fits the profile?
It fits the profile perfectly. If it walks like a duck and quacks like a duck. Or in this case, if it twists light exactly like a solar flare.
It is probably a solar flare from a neighbor star. I just want to clarify something for you, the listener, though. We didn't see this companion star, did we? We didn't take an optical picture of it.
No, absolutely not. At 2.5 billion light years, trying to visually see a standard star sitting right next to a bright, flaring FRB source is basically impossible with current tech. It's too far and way too faint compared to the burst itself. We saw it through its influence.
Through the mess it made.
Exactly. We saw the plasma it threw out. It's like seeing footprints appear in the snow. You don't see the person who made them, but you know for a fact someone just walked by.
That's a great image. Or seeing leaves rustle in the wind. You don't see the wind, but you see its effects.
Precisely. And we should mention this wasn't just fast working entirely alone in a vacuum. Australia's Parkes telescope also contributed continuous radio observations, which helped verify these findings. It was a real cross-hemisphere effort.
So we have the evidence, we have the culprit, a messy neighbor star. What does this mean for the big picture? Let's move to the implications here. Why does it matter so much if an FRB has a buddy?
This is where it gets really fascinating for astrophysics, because this discovery helps solidify the identity of the FRB source itself.
The engine.
The engine. For a long time, the leading suspect for what creates FRBs has been a magnetar.
A magnetar, which is arguably the most metal thing in the entire universe.
It really is. A magnetar is a type of neutron star, so it's the crushed, collapsed core of a dead star, and it's incredibly dense. A single teaspoon of it would weigh 1 billion tons.
1 billion tons.
But its defining feature is the magnetic field. It has a magnetic field that is trillions of times stronger than Earth's.
So strong it would literally rip you apart at the atomic level if you got anywhere near it.
That's the one. These are extreme, extreme objects. And the kind of energy required to produce a fast radio burst fits perfectly with what a magnetar can output during a starquake or a magnetic reconnection event.
But there's been a puzzle, right?
A huge puzzle. If all FRBs are magnetars, why do some repeat and some don't? Why are some one and done while others, like our friend FRB 220529A, keep flashing over and over?
That is the million-dollar question. Is it a different type of star, or is it just in a different situation?
And this discovery of a binary system points directly at the different situation answer.
The relationship changes the behavior.
It could be the key.
Yeah.
Professor Bing Zhang proposes what he calls a unified physical picture. The hypothesis is that perhaps all FRBs really do originate from magnetars, but the ones that repeat, maybe they repeat because they are in a binary system.
So the partner star is somehow instigating it or enabling it.
It could be a number of things. The interactions in a binary system might create a preferred geometry or a specific environment around the magnetar that makes the bursts easier for us to detect repeatedly. Or maybe the companion star is feeding material to the magnetar, which fuels more frequent bursts.
Like stoking a fire. The isolated magnetar might have one big flare-up and then it's done, but the one with a friend keeps getting more fuel shoveled into the furnace.
That's one possibility. An isolated magnetar might just act very differently than one that's constantly interacting with the companion's gravity, its stellar wind, its magnetic field. It completely shifts our understanding from thinking about these as isolated stars screaming in the dark to, well, stellar relationships.
It proves that FRBs aren't just random, isolated explosions. They can be complex interactions within a dynamic system.
It makes the universe feel a lot more alive.
Yeah.
And interconnected. It's not just static points of light. It's systems, it's orbits, it's weather.
It's stellar weather. And we're just now learning how to read the forecast from billions of light years away.
Exactly. We used to think of space as this mostly static backdrop, but this shows it's full of events, flares, ejections, interactions that happen on human timescales. Weeks, not millions of years.
So let's just take a moment and summarize this win for science.
Yeah.
Because this really feels like a victory lap for the whole team involved.
Absolutely. This is a triumph of collaboration. You have researchers from HKU, Purple Mountain Observatory, Yunnan University, and the University of Science and Technology of China all working together on this.
Professor Shuifeng Wu, who was the lead corresponding author, specifically mentioned the tireless work and persevering observations. And I think we really saw that in the story, that 17 months of watching and waiting.
That's the perseverance right there. And we have to give credit to the technology. This discovery was only possible because of the extreme sensitivity of FAST, the China Sky Eye. You simply cannot do this science with a smaller telescope. You need the world's best sensitivity to catch a detail this subtle, a tiny twist in the light from 2.5 billion light years away.
So, looking forward, what's next? Now that we know at least some FRBs are in binary systems.
Now we need to know the statistics. Is this a fluke? Was FRB 220529A just an oddball? Or is this the standard model for repeaters? Continued monitoring might tell us how common these binary systems are.
Are most FRBs married to another star? Or is this a rare couple?
Exactly. Is this the exception or is this the rule? We just don't know yet. We simply need more data, more stakeouts.
More staring at boring stars for months at a time, just waiting for them to do something interesting.
That's how discoveries are made.
Well, I think this whole exploration has given us a completely new way to look at those little flashes in the sky.
It certainly has for me.
Let's synthesize this entire journey before we let you go.
Yeah.
We started with a mysterious flash, a cosmic flicker, from 2.5 billion light years away.
We had a massive telescope in China staring at it, unblinking, for 17 straight months.
Then we saw a sudden 2-week twist in the signal, that RM flare.
And we used that twist to realize that a neighbor star had, in effect, sneezed a cloud of plasma right across our line of sight.
A stellar sneeze caught on tape from across the universe. It's an incredible story.
It's a reminder that the universe is just so dynamic. Even things that seem stable, like a repeating signal, can be subjected to these sudden, violent weather events caused by their neighbors.
It really makes you think. If we can detect a star sneezing from 2.5 billion light years away just by looking at how it twists a radio signal.
It raises a pretty provocative question, doesn't it?
It does. What other invisible events are we missing? What else is happening out there in the dark between the stars that we just haven't built the right filter to see yet, simply because we aren't staring at the right spot for long enough?
That is the question that keeps the next generation of astronomers employed. And it's exactly why we keep building bigger and better telescopes.
Thank you so much for breaking this all down with us. It has been a really fascinating look at the binary secret of fast radio bursts.
My pleasure. It's always good to look up.
And to you, listening, keep looking up. You never know what you might see if you just stare long enough. Thanks for joining our investigation today.
Goodbye for now.
See you next time.